are back to work. Now there is something which is good, that we have a lunch break afterwards, because John is going to tax us.
Yes, that's right.
Yeah. Guys, come on. Like children.
Can you start recording?
Children, please obey.
Yes.
That's it.
We're herding the cats down here. Pushing the barrel full of frogs. Okay, John, can you start please? Because things are fluctuating.
Hello, everybody. Good afternoon.
Hello.
Hello.
Hi.
What I'm going to talk about today is I'm going to talk about
We've got problem with volume, yeah.
volume.
Yeah, volume up and speak slowly so it's distinct, because it's really, that's one of the problems of coming over on Zoom.
Okay. Right. I'm not sure I know how to turn the volume up.
That's okay.
Maybe you just need to be near your mic.
I'll speak louder.
And speak louder. Yeah.
Testing.
Yeah, it's okay, man.
That's okay, yeah, just speak loudly.
Radio, I can do that. Just pretend I have 400 students.
That's right.
Right, what I want to talk about today is advancing relativistic quantum mechanics. What's required to get to a theory which is actually useful to do engineering. And one of the sub-topics is what is the proper basis of quantization? The various kinds of quantization we have, charge quantization, spin quantization. What are the bases of those? Often we take quantization as an axiom, but where does that thing come from physically? Because that's the two themes of the talk. And this talk is based on work that I've been carrying out with Arne and Ben in California. But the original theory was developed by Martin and Marek and myself. And there's a lot of this done up on the Bicycle Society website, bicycle.com, if anyone's getting back to this stuff. And loads of publications are on there as well. So the kind of thing I'm going to be talking about today is a new theory, and that new theory was initially developed to extend electromagnetism to something that could self-confine the electron field. So Martin and I came up with an idea that the electron might be described as a self-localized photon back in the early 90s. And we published a paper on a model based on that back in 1997. However, we were researching during that time, later as well, for a way to the one thing that was missing from that model was a reason why the photon would go around, why a photon might go around and around the surface, what could self-confine it. And in about 2014, we came up with an idea of a theory that would do that had the necessary confining force, and I'm going to talk a little bit about that during this talk, or the necessary confining element. The element is a big word for it. So we're going to look at the elements of elements. One of the elements of the elementary particles, what's the internal structure of elementary particles, electrons, protons, neutrons, photons, atoms as well, all the world around us. So the picture you see in front of you is a dielectron boson. It's a pair of electrons which are wrapped up in one another, both going around an internally toroidal space, a momentum space, one going left-handed around that space, the other right-handed. The left-handed rotation being the spin-up electron, and the right-handed rotation being the spin-down electron. Now that's a dielectron boson. To do a particle to either an electron or a spin-up electron or a spin-down electron, because it's a boson, the bosonic particle. That thing which is responsible for superconductivity, for example, or if you like, the inner shell of a helium atom. The helium atom is a very interesting thing. It's really a triboson system that has a pair of protons, a pair of neutrons, and a pair of electrons. Each kind of boson entangled in my view. We'll come on to some of that depending on how fast I get through this hour's talk, we'll see. So, first of all, what kind of think the new theory is required to describe that? Well, I think we need to go beyond the just energy that we've used for the last couple of hundred years, so just a Hamiltonian or a Lagrangian system, which is based on something which is certainly true, conservation of energy, or balance of energy, the rate of change of phase in the conjugate case. Both based on just the energy in the system, and then define a phase in terms of something like a quantum mechanical wave function, something like 5 is equal to A to the ikx minus omega t, where that's actually something that one has put into the theory, and then one has used that. So you have a single plane, it's e to the y concept, so a quantum wave, but that wave is then described by such things as x minus omega t in momentum times the wave vector and the energy times the frequency. So these are both action coordinates. So one needs to go beyond that, because that's been very good so far, but I don't think it's really quite enough. One needs to get to a proper underlying theory of these states. You might think the relativistic quantum mechanics sounds Dirac theory did that, but it doesn't appear to do. It hasn't proven useful. It hasn't proven useful in the engineering sense. In engineering stuff, when it doesn't quantum mechanics, one doesn't use the Dirac theory, it's short with the other, because the Dirac theory is just too hard to calculate with. It seems to sound somewhere. It doesn't seem to be quite right and quite full. The question is, if it's not quite right or what's quite full, what is? This is a proposal part of the subject theory. So the Maxwell part of this is, and it always was, fully relativistic, even before Einstein came along. And hence his use of thinking about light in a box to start looking at the basis of relativity back in the early 1900s. Maxwell alone, the theory of Maxwell is not complete, it's a set of equations describing the field, but it's missing quite a lot. It's missing, in fact, well, one of them, but obviously missing, is quantization. Another thing it's missing is it's only as it stands on fields. It doesn't have the gauge part of that, which has been developed largely in the 20th century. And doesn't really deal with, it deals with spin to a certain extent. And spin is, or at least the laser versions of that, managed to do that in some parts of the field theory. But it hasn't done it in a fully rounded way yet in the developed level. He didn't invent this in a familiar vector algebra. He developed it in quaternionic algebra, a left-handed quaternionic algebra, which we talked about a little bit in the previous talks. The approach was largely dropped because it was too obscure and too difficult for students to learn. And Heatherside came along and developed a vector algebra, which Maxwell agreed was easier to learn. And things really progressed into the kind of vector algebra we look at. But for example, Peters just mentioned, as he's trying to do that, we find that the kind of things that appear in the Dirac equation are not really vectors, or even more than vectors, they're different vectors. And the vector algebra is fine, it's not relativistic. It's relativistic. A lot of things in that is vectors. Point minus c plus point minus c is not what it is, c, it's available. So the vector algebra, it isn't. It's something more than that. I think the problem has persisted. Like developing Microsoft Word, you end up with something which is really rubbish. Because everyone uses it and stuck in the shit. So generations have been teaching our students to really not think properly and think about what's required in terms of the basis of reality. And remember, also the Dirac theory is 19 years old, but really time for a bit of an update. It does introduce spin. The way it introduces spin is into solutions and spinners. And this makes it very difficult to think about the kind of mysterious things that have a property if you really come back to their starting point, if you're taken through 720 degrees. So we've got something like ways of thinking of engineering new systems, and we need to do that and do that. So the result of this is that if one is to quantum quantum systems, one decides that one has up until now designed those things pretty much in terms of Schrödinger, so it describes material systems in a solid state, for example, where. So let's just get off the quantum systems calculated and Schrödinger theory of using. So Dirac, bottom line, Dirac Maxwell and Schrödinger are great, they're very good up to the point, but it would be kind of nice if we knew what we need a proper theory of spin thinking. So we're thinking about things that rise to the underlying elementary particles and their quantization. So here's a proposal. But let's first talk about one Dirac quantum mechanics relatively useful. These theories are on the right-hand side of the theory. So, what is Dirac? Well, if we ignore such detailed as maths and school theories, we write it as either these functions and some wave function psi is equal to 0. So what we got on the left-hand side, we've got an operator equation. So it's the operators, as Peter was saying, the operators are important thing here. That psi is going to emerge from the Dirac field, has a zit of the wave inside it, a zit just a German word. Most words in physics are English. It's one of the few words that are German. Zip just means vibrating. And vibration just means motion. So it just means vibrating motion. That kind of solution, one can integrate the gravity function. One doesn't get an e to the I x on top of t, the wave function. One gets a vibration in all spatial and temporal directions. And that's what the zip debating is. People are asking about. But looking at the structure of that equation, I d slash minus percent of size equal to what are these things? Psi is going to turn out to be as a spinner in terms of the solution to relativistic quantum mechanics. I squared minus 1. N is the mass, it's a lump of mass. And d slash is the implicit one. What that is that's d by dt minus d by dx minus d by minus d by dz and the plus minus minus metric. So it's a full vector differential. And that's the direct equation. But look at it. You've got a distinction between what's happening with the operator part, so it is by the energy and the momentum, the d-slash part, and the mass, which is kind of just in there as a lump. Now, I think it's done better than that, because when you look at physical equations, he's stuck quaternion part in terms of mathematics, and he's got something which has got some form, which is a little better. That's one of the developments, it's one of the directions of development that might be required here. Now, I'm going to do that slightly differently. I'm going to use a flipped algebra, and then come with stable algebra. That's also a revision algebra that goes one step beyond quaternions to describe this stuff, because this algebra is introduced by Professor Butler, who science people know it, so it's really kind of using that PhD and from stuff back in the late 90s. And it contains a bunch of people. It contains complex algebra, it contains quaternion algebra, but it also contains the Lorentz algebra. It is a direct algebra, which is called sometimes the direct flipped algebra for that reason. But it doesn't contain the scalar square root of minus 1 by itself. And if you use that algebra, you can write the equation on the right hand side of that, which is a simpler equation. That d mu is pretty much the same as the d slash. It's d by dt minus d by dx minus d by 1 minus d by dz. But instead of having a complex number there, it just has the gamma matrix. Gamma 0, gamma 1, gamma 2, gamma 3. It contains those direct matrices. Those direct matrices are not vectors. Maybe expansion or genesis. Then the 2x4 matrices. And their tenses. They're matrices. They're matrices. Not worry about it. And so it's like a full vector. It's not multiple vectors. It's not in vectors. As is and that psi g sitting there is a general field. The psi g contains the electric fields. The but it has a lot of other components as well. And what I'm going to do is those 16 components complementary forms of four-dimensional space. So I take four-dimensional space now. There are 16 different objects which are conformed from that and multiply things or dividing. So for example, if I divide anything by itself, I get the number 1. So that's the thing to begin with. Anything divided by itself. It's a scalar, it's not a calculation, it's just a scalar. So that's multiplied. I can also multiply them by each other calculations. I can multiply by it's component by the y component, but an area, it's something that's like an area of the resource. And that's a different thing, it's not linearly dependent on x. So I have a four-dimensional algebra x, y, z, a three-dimensional algebra x, y, z. I can form things which are not x in meters or y in meters or z in meters. There are x times y in meters squared, from objects which are essentially areas. In the Fordian space, I found there are 6 of those because you have 0, 1, 0, 2, 0, 3, also 2, 3, 3, 1, so 6 combinations of 2 objects like 4, or 5 objects. And those turn out to be the fields in this organism. So if I just take those 6 objects and stick a four-dimensional operator with a direct matrix into it, what I get out, I get exactly Maxwell's equation. Just all 4 of them with the correct symbols. So that d mu psi g contains the Maxwell equations. There's 6 equations out of 16. What are the rest? I think the equation on the right is, the rock equation is very real. It's simple. It's also the d-slash is kind of what you would expect. That the d-slash does contain an ideal with a vector summation that is not. It really just works on compact matrices, whatever they are. And that makes sense. Now, looking at the sub-algebra is a larger algebra. Complex algebra, if you think about what we're actually using for complex counts, we're using a two-dimensional system where one dimension is expressed to +1 and the other to -1. It's too simple. It's not non-commutative as nature is. It doesn't copy and compress the non-commutative 3D space. It's never going to fully describe nature. It describes an aspect of nature. Now, because it's properly distinguished from that field equation, from the graph equation, the distinction from n and the operator is the square root of -1, look at it. It doesn't distinguish it properly. It's part of it, but not enough. And it's not quite, it's simply quite close enough. Look also at the mass in here. It's called an ad hoc. It's not a dynamical variable. You decide, for example, in spinner space, it has to, because the kind of things you get when you integrate solutions are great. They come back with a starting point up to 720. That's the formula which Carpenter students introduced in the 30s. And the fields are really in there in that equation. It's the objects on which it operates are not field vectors, not spin, not current, they're spinners. Which, if you want to extend them directly, you can bring the field in and so, how can we do better? Well, if we take psi, psi here on the right hand side of the top, physical field, then the set of variables that have naturally transformations which we can calculate. So not constant that deals on transforms field as well as surprise. The vector part transforms into full vector. Why? It's actually we put into it. For the vector algebra has that structure. That's the nature of the direct Clifford algebra. It's a relativistic algebra. The scalar part, the one that's only looking at more like 7, is invariantly having a Laplace transformation. It transforms like a mass or an energy. So one has things that transform as a mass or less mass, things that transform as a core vector, things that transform as an electromagnetic field. It's also useful when we identify the mass or vector of the electromagnetic field, like it says. But if one does the trivector stuff, they want to take something which is called a momentum, which is a dx by dt, which is constants from the x direction. Now, what is most positive perpendicular vector, we have a rotating vector, something that does essentially r cos p. One has an angular momentum. And the elementary angular momentum is described by the trivector elements. So we now have an algebra with a rest mass, with current, with full current, with a thickness field, and with angular momentum, a spin, internal angular momentum. The range of components, the fourth-dimensional hedgehog thing of 4 indices, turns out that the translation properties of that transforms also as a rest field. So the scalar and the dual scalar, the two scalar, form something which is also complex numbers. One space and one small space, so it takes us to one thing that's beginning to look like a multivariate structure, which we might fulfill, might be an axiomatic basis to build the sixth problem. That's a completely characterizing the outline there. Not yet, nonetheless, maybe a step in the right direction. So if I look at the subsets, du, psi, nu, and phi vector, then turn to turn I'll show you the part which we equations. So, what am I proposing? I'm proposing a set of equations of motion with a mass field dq. These are they, du psi g equals 0, du psi g, like a complex field. And the proposed motion is of the sub-quantum field, don't quantize anything there. This new theory is and provides hitherto unprecedented language of thinking inside particles, thinking of physics of steel, of spin, of current, of mathematical mass, and of the relationship between you get field, you get field, you get the currents by differentiating the field, you get the field by differentiating the electric potential. As is known, dA is F in tensor field theory, and dF is J in Maxwell's equations with non-technical J is in Maxwell's equation. So it's a ratios to do in terms of the measure that one of these pretty much everything doesn't work on explosions. So these are the proposed new equations, and the hope is, of course, new thinking leads to possibility of new materials, devices, and engineering, not partly something that's drawn into this talk. Now, well, it's one thing, let's talk about this nothing to do. And you're talking about going through an interesting reason in terms of the simplicity of nature. But something that's important, when you set up the structure and various chemical substances, if you're doing a differential, you can do a left differential or a right differential. Like you can do d by dt of in the x direction, or you can do x times d by dt. You can put the differential before or after it's ordered. And those are not really matters. So you can put it before or after, so you can do left-handed differentiation or right-handed differentiation. Or you can take a commutator, choose them both, and do what's left over. And because it becomes more complicated, the right terms are left over, in fact. So one can do any of those three things. One can say, is it ordered? Are we looking at something in terms of a division, or a division of a small thing? Or are we looking at taking something and then dividing it? That matters. We also look on less things that commutator function, we're not just a whole change the sum. It's not. But before you think about what, we do differential all the time, we've been learning this since we were in school. But what does it mean to divide something by something? What does it mean to divide space by time? What does it mean to divide a ruler by a clock? Is that a sensible thing to do? You know, it is. If the x by the t is a velocity, you know what the velocity is. That's all the time when you're driving around in a car or on your bike. But what is division in that context? Division between, what's 6 divided by 2? It's 3. You know what that happens. We divided 6 into 2 parts, we've got 2 3s. But what's a meter divided by a second? What's actually happening in the physics of velocity? Now, so what are we doing? Well, let's think about it. The key is that there are 2 spaces and 2 times in which one is living at the moment. One lives in space and time, and one exists in inverse space and inverse time. Where one lives and where one exists are 2 different space-times. What do I mean by that? Think about it. Think about quantum. Think about E is h nu. Energy is Planck's constant times frequency. That's a quantized idea. Energy in the photon is proportional to the constant times its frequency. Frequency is inverse time. One exists in inverse time. No inverse time and more energy. More inverse time, new frequency, bigger energy. Less inverse time, smaller energy. One is mentions of inverse time. Likewise, quantization occurs in not space, but inverse space. E is Planck's constant. E is h bar k. So we just have to the wavelength. Wavelength gets hallucination in space. Your existence is not in space and time, but inverse space, inverse time. Having to move around in place, which is space and time, and from place to place in space, which is continuous, and time, which is continuous in two directions. So really there are two spaces here that I'm sitting in that are identical to one the unit level in this space. Yes. So the sign identical to one another. So that sign is the metric. So time and inverse time, an inverse unit time and a time, are taken to be the same vector in Maxwell's equations and will be taken to be the same vector here. Space and inverse space are inverse, the negative. Here's a plus minus metric. It doesn't need to say plus minus metric, you can say that it's the other way around, you can get a minus plus metric. That turns out to change the set of things which spur plus and minus one in their calculations are introduced. I think one is correct, that's the direct thing, plus minus, and the other is incorrect. The first person took that, the comments of that actually filled up in the statement, it's simple, which is we can pick on so inverse times frequency, space, characteristic wave is kind of a local ruler character, something which defines the size of the object which we're thinking about. It's a unity for whatever that object is. Quantized energy is an inverse time, quantized energy in inverse space. Also, if you do that dynamic interaction between things where a transaction is involved, so particular complementary dynamics, where there's an interaction, it's a packet of energy, then the process of emission of something which is scalar energy both in terms of it being a vector, but also in terms of it being distributed throughout space. It has some distribution issues, very fundamentally the linear stream. Then one's talking about a very complex object. In order to turn a complex object in space-time, not inverse space, inverse time, both in space-time and in space divided by time, dynamic space, scalar, we need to invert both the mathematical form of that and the extensive form of that. Needs to find an inverse of the 3D object. And that sounds complicated, but it's not really. You just take the unit level, which you know what it is, because it's your velocity. Draw a circle or a sphere that size, and then take any point within that sphere and find its inverse by sending it in the same direction and changing its third of the way along. Then the inverse is at 3. If it's 3, the inverse is 5, the inverse is at 5. So one could do those equations, it's a conformal mapping, well known, widely studied and current before computers were down, it means to solve the differential equations. So well known conformal map. And the conformal map, for example, a bunch of circles on the left of the screen here, is a bunch of bicircles on the right of the screen, which we were taking around the y-axis of the sphere, and on the left side of the sphere and on the right side of the torus. So there's a sense in which spheres and tori are inverses of one another. Something which is spherical in space is taller than an inverse space and vice versa. So we're talking about these two different spaces. What we're going to do is we're going to form not what Dennis was calling a superposition piece, because he was talking about addition. We're going to multiply these. We're going to multiply a little bit. So literally, a bit of stuff divided by a bit of other stuff. A bit of space divided by a bit of stuff. The x by dt is the velocity. Right? Okay. So dx by dt measures the little bit of space divided by a little bit of time. A little bit of time multiplied into space. And the order difference. So if you commutate it, you just get that little thing. Change the sign and change the sign. We're also showing you this first. So that's where velocity comes from. You're really looking at a multiplication of space by inverse velocity. Element of space multiplied by inverse time multiplied into inverse space is a velocity. It's going to be twice the velocity. So it gives the number system. So, there we are, one of them. So that's what we're going to do. We're going to do those things. We're going to form, when we do the differential equation, d psi equals 0, we're taking I divide it to the number shape and multiply it by extending space. So I have a product within the first space, I, with a space time. Elements in space time as well. So it's a Australian equation and the direct equation looks more than these equations really are. Some equation just some sort of description of reality, something in reality. What's happening in reality isn't reactions, interactions involving reactions. So it's only when you convert something which is complex to something which is simple, something which is multi-dimensional in the dimensional sense, and multi-dimensional in the mathematical sense, for something which is simply a scalar has to be something like this. The spatial distribution and the temporal distribution and the play distribution nature is multi-vector nature, whether it's real or complex in simple quantum mechanics, or whether it's more complex systems such as the one we're talking about. So, the differential dynamics needs to order on the two space and show that. So here's the theory of this. So let's just do it. But on a page, it's not. So no lot of you will not be distracted. So what we can examples the gamma, which is gamma 0, gamma 1, just what the field on this side. Sorry. I'm mixing the sides of the field, but it's all together in the last one. So, notation from gamma to alpha scale. I think that's the alpha scale. So
John, could you speak up just a little bit more? Because I think we're having trouble quite hearing you at some point.
Yes, I'll be delighted. So, and then we're multiplying it by this 16 component object, which is this psi g, and there it is out in all its glory. So there's the first term is the scalar term, the next 4 terms are the 4-vector term, the next 6 terms are the field, the next 4 terms are the angular momentum, and the last term is the hedgehog, the 4-dimensional directed volume. So it's a 4-vector, it's one element root, which has the convention of the square root recipe, so it's square root energy, over 16 linear independent space-time configurations. So it's a bit more complicated than equations that you're used to. It's similar to Maxwell's equations. If we just take the subset with the sine newtons with the fields, we get exactly just the Maxwell's equation. So if you imagine that being sort of extended Maxwell equation. So this is the equation for quantum fluid. And there it is, that's the full equation. On the left-hand side, all its terms. So I've got 4 times 16, which of course, quick calculation will give 64 terms. There they are on the left-hand side. If you look at them, you'll find that they follow the form, fully 4-dimensional algebra, but you'll find the patterns of div, grad, and curve in there as well. The same patterns of curve in 4-dimensional div and curve in 3-space vector algebra. Which is why we were able to use 3-space vector algebra so successfully for over 100 years, because they're just the same. Well, space and 3-space are very similar, which is part of the reason, in my view, that we live in a 4-dimensional universe. Anyway, if we translate those using those patterns, so on the right-hand side I've just written down, I've extracted the div, grads, and curves. And the first 4 equations, if you ignore the p's and q's, are exactly the Maxwell equations. P and Q are like less massive Maxwell equations, and the last 4 equations are new on the right-hand side. What they do is, in place of relating electric d by dt to curl V, like in Maxwell's equations, we relate dA by dt, the tangent of the vector potential, to the curl of the spin. The new equations are the constraint equations on reality that fix the gauge to the spin. There are actually 2 gauge equations in there. It's a double gauge equation. Look at the 5th equation is just the standard Lorentz gauge equation. There's another one, the last equation, there's another gauge equation. That gauge equation just contains the spin and the sorts of the spin. The gauge equation, so there's a Lorentz gauge there. The 5th equation is just the Lorentz gauge, that's equal to 0. And the 8th equation is a spin gauge, second gauge. Now what the gauges do for you in standard theory is Maxwell's equations are unconstrained. There are too many solutions. Put a gauge equation in that reduces the number of solutions and makes it easier to solve, which is why you can do it. Here, this makes it easier to solve the gauge equations when you have another gauge equation. The other two equations, the 6th and 7th here, are like the Maxwell's equations of spin vector potential. There are further constraints on the form of the spin. The spin has to be circulating, and the vector potential that has to be around and around the surface too, which is kind of what we want when things defined in a particle. So that's what they are. I apologise for the maths, but it's all there if you look at it. Here's a picture of what's happening. So these are a bunch of boxes describing all of these different terms. So along the top set are the 16 different components. First one is the scalar, next one's time, then x, y, z, then magnetic field in x, y, z, then electric field x, y, z, then spin x, y, z, etc. And I've looked at these things in terms of what I put in the boxes is looking along the top row. The second box along the top row is isomorphic to quaternions. Those things are, if I just take that box, that's the second box on the top, or the second box down on the top left, those things are isomorphic to quaternions.
No, yeah, I was just pointing to the box you mean on the screen.
Thank you, Ollie.
Thank you very much. So now it turns out that all the other boxes can be derived from those two boxes by multiplying by one of the single element terms. So for example, if you multiply that box by the time, by the alpha 0 term, you get the fourth box on the top, which is the spin set. So they're still a bit like quaternions, but they are not quaternions because first of all they're not. It's not a complete group. You multiply the spin for one of the source groups. So you can use that to generate all 16 elements. It doesn't remain within the spin of the group, whereas multiplications and divisions within the quaternion group, within the magnetic field type group, do remain. So there's a structure to this, and that structure is almost fractal. There's a full 4D algebra. That 4D algebra contains a bunch of copies of the quaternion algebra, 3D algebra, and which has a huge implication because it's the Maxwell originally developed as the theory, for example, and which Peter is championing momentarily forward in all sorts of interesting directions. It contains the complex numbers on top left or bottom and bottom right, the scalar and the top left and top right, or bottom left and bottom right. That pair is complex numbers. There are a bunch of things that are nearly copies of quaternions, they're not quite. There are the quaternions themselves, and there's the full 4D algebra, which is being used to set up the language. They are. And that's the equation I've done. Right. So, we'll expand this as well. We can do a 16 derivative of 16 variables for reference, so we'll talk to you about that. So that's his theory. What can you do with it? So that's a number of field theory, let's have a look at what we're doing. Let's reason over what it is. It's 21. So, let's move to that. One can write down solutions. So, well, what's the solution? The psi g is equal to 0. And here is one on the top. This is equation. It's complicated. It's complicated. It's a two-component wave function. So it has two phases. It has a different phase for space and a different phase for time. But what's interesting about it is the thing is quantized. It's quantized in the sense that everything in this thing scales with a single parameter. A single parameter, so with a single h0, this describes every photon in the universe. All photons have been got. The thing is quantized in terms of a single parameter. And also it has a fixed angular momentum. If you calculate the angular momentum around the axis for this thing, then it's a fixed number. It's number being possibly h bar. It doesn't give you h bar, but it's a fixed number. There's a good. Also, this thing transforms relativistically. If you transform that thing relativistically, any photon scales exactly relativistically. So there's a way to function. You can get other wave functions as well, like wave functions, just like that down. You might want something which it's used in something called absolute relativity. What I mean by that? What I'm doing here, I'm not allowing anything to be left which isn't there's a mathematics which allows one to do that. And the converse to this is in that mathematics, and not allowing anything which doesn't have its proper relativistic form to be written down at all. Otherwise, that mathematics is not a proper representation of reality. It's a complete reality of the truth. So look at the top left wave function, I've written alpha 3 kz, alpha 3 is an vector in the z direction, minus alpha 0 over t. These are direct matrices, and they're in there in space and time. And the direct matrix in space is different. And these things are very difficult to do as you go through the applications of some of the maximum way in the wave functions around these wave functions. The next wave function, then, is the electron, what I think might be the electron wave function. It has 4 components, and it has, what waves and what's moving in? Well, in the wave function we just saw, it was field was waving into fields. Here we have mass waving to fields. 4 components here are the 2 resonance components, 2 field components, electrical magnetic field and resonance. So what we have is the wave, electron wave function. There's a wave where dynamically the mass is involved. The difference between Dirac and Williamson-talking the mark is in Dirac the mass is just the lump, it's put in there because you need a mass. Here, the mass is put in as a dynamical function in the same status of the fields, and it interacts with the fields, and it confines the fields. If you look at the forces here, which are probably they have time to do with the mass what they do is they make light, electromagnetic radiation, around circles, the same value which you do in the wave function, equals around twice. So you end up with 4 solutions for circulating light, which I was going to talk about quantization of these things. I'll talk about. I can't really do proper justice to talking about quantization in 5 to 10 minutes, but I'll go over it very quickly. What is quantization and what's happening? Well, the main reason quantization happens is because we're talking about waves. What quantization is in this sense of roots. The simplest parallel to quantization is where the sound is what has a wave, and assumes it has a wave, and that's the way form of the wave in simple quantization. But here you have a wave because you know what's waving between what and what, because that's what the field equations do. Come back to observations, for example, you know how that works. And here they work more simply because you have the first order equation and all the elements of that wave, not just written down some wave functions for that. And if you have a wave, in order for that wave to represent something real, it better have the same value when you come around full circuit. It's the same wave. So all the quantization condition means is that you have an integer number of the wavelengths, so the thing is coherent in the sense that if it's not coherent, it doesn't exist. It coheres itself to death. So quantization emerges essentially from waves. This theory shows what kind of waves, so you can understand what we call that quantization. That's the quantization of voltages and stuff like that, and many quantizations you see. The quantization of angular momentum comes from the fact that all objects have the same momentum, which is talking about all the same, which is for each of the others, or the range space functions. One also needs something else. For something to exist, you need to have a phase coherence. I've said you have 2 different phases here, one in space and one in time. Well, that's fine, provided they keep on coming together and reinforcing one another, provided they're harmonic. This is de Broglie's harmony of phases. And for those of you who don't remember and know what de Broglie's harmony of phases was, before quantum mechanics there was de Broglie. And de Broglie, using relativity, to arrive at a relationship between things that happen for what the relativistic law of change of energy transformation, and the change plots, change not slow down, you can see speeds up. Well, no. Okay, what are the plots and oscillators? So how can an oscillator both speed up and slow down, which was these pieces for? Well, luckily, the boy was a genius, so he worked it out. He came through this idea of the harmonic phases, which led to his famous relation, non-rotary oscillators, okay, so that came from a problems in relativity initially. With his thesis, it's beautiful in French, but practical stress in English, which is good to read it and smell. So for quantization, the basis can match to 2 pi units for bosons. There has to be 4 pi for fermions because those loops I showed you right at the beginning were around twice. So quantum forms in spin space, charge quantization is electric field space, flux quantization is a magnetic field space. These are separate quantizations which all happen. And those and these, so you have H bar, you have E, and you have H or you have magnetic flux, charge quantization, and spin quantization, which are different spaces. And mass quantization occurs externally. Peter was saying that the force of the nuclear is about the time. Yeah. What some considers electric is about the nuclear. So depending on the size of it, that's what you need. And what these forces do with the force that are interactions with the rest of the universe, basically, with their existence. Their existence is bound up with their zero energy status, with their zero energy cell as a whole. So that has to balance somehow, balances through voltage, and that would equals MC squared interactions. So what's more is quantization, that can numbers, quantum quantization, and many quantizations. They all rise in the same kind of way, like harmony. So you can get the sort of has to recreate itself every cycle. So these are medicine sets, so let's see. So I was going to show why overall the actually possible smoke around these vertex but there's a light box like that, the last equation there. Second last equation is the one that everybody uses. Actually, where that comes from is it comes from the partnership of protons in a box. We'll write it, it's in the paper, June 2019. Charge quantization. Charge quantization, we'll talk about that. I'll just say briefly where it comes from. The thing is that if one has an object which has an angular momentum, it has an angular momentum h bar, projects have an angular momentum h bar. Take that thing, spin it around, make it bite its own tail in a single wave. You have one energy, one is h mu, and you have a field, and that energy you can describe as the field. The field is half x on e squared plus half x on c squared b squared, and that's how it works. So if you look at what the field strength is, you know that it's there on the left side of the alpha direction from the capacitor. So it's twisted it, so we know how much field has at what distance, so then we calculate the charge. And as we calculate the charge, it comes to the charge, which we did in 97, this is 97 paper. And the number you get, nobody surprised, is the electrical charge in percent. It's actually a few percent smaller than electrical charge right up on top of itself. And as one expands it, so we use field all around charge. One would observe increases the frequencies to about 50 times the electrical charge. But apparently the electron sits there, but it's not playing, it's not just like being completely on top of itself. Pretty much like the first slide I showed you. You have something like that. That toroidal thing is in spin space. Electrons are known to be a large spherical symmetric. Tori are projections of a fourth sphere. Everything is spherical, and what we observe is something that's converting the free space. So, that's charge quantization. To get matter, you find light into matter, you stick it into a set of nested Tory like that. It's created with this, here's a possible decoration of electron. Two photons to electron through there. That's what's the level of the theories. That's what a single electron looks like in spin space, in field space, and in real spatial space being the thing in the middle, and those are things around like that, so we won't. As we talk about chemistry and how that works, it's superconductivity, electric field space, field space, spin space, and how they interact. I was going to derive the Pauli principle for you and say that it isn't a principle, but it is a force, it's a very strong force. That's in a paper in 2008, which is there. No, you can see what it is to work. By electron balls and lots of activity work. Spherical harmonics and how atoms work. And spaces from obsolete ones. And what happens with atoms. And what happens in crystals. I think I'll say something quickly about this. You see, electrons are very mysterious objects. They're quite small, and culture records about 10 to the minus 13 meters. In atoms, they're much bigger, they're about 10 to the minus 10 meters. If you look in the solid state, the electrons in the solid state, they're much bigger. Again, when I was looking at single electron devices, the size of a single electron was, a single electron in a gas-algas tetrastructure is roughly 40 nanometers across. Nanometers. These things are almost visible. How do electrons do that? How can they go big and small? How can they be so immense, elastic? Given energy physics, when I was working at CERN, we're smashing these things into particle acceleration. They see they're 10 to the minus 18 meters, but they can't be because the charge of 10 to the minus 18 meters will pack far more energy in that in its field than it has mass. They can't be that small. So there are contradictions there, but they do that. And we understand what the economy is quite interesting. That's just very conclusions. Conclusion is a new reference to quantum mechanics here, which we like chemistry. Theory is an extension of Maxwell, it generalizes the graph equation, and it underpins 3D. You got that. The thing is that there are two aspects of charge. Charge is either a field, or one aspect of it, so it's an exchange. It's a unified, so it's two approaches. Understand exchange and fills with this. With this thing with the flow we talked about the space-time inverse space at the moment with the scope theory. And what ends up in forces within those free spaces. And there are component space between these spaces. Visible, very visible. Despite that,
Okay.
Thank you.
Thank you. Questions? Comments? Yeah.
100. So if I understand you correctly, near the start you said the 4 pi relates to the radius or the radial relations in the torus, and so how you're modelling the electron is it's kind of making 2 revolutions of 2 pi while it's rotating around the other radius of the torus. Is that a good way of putting it? In your last diagram, it looked almost like a Mobius band, one complete edge making 2 revolutions.
Yeah, I'm not putting it in, it's coming out.
Yes, that's right, yeah.
With the other rotation, so here's a belt.
Yeah.
Can you see that?
Yeah.
The rotation of, so the relativistic belt, that radius is now, if I take a single wavelength of lambda, that diameter is, that radius is lambda over 2 pi. If I could twist it, so I could twist it, so that's modeling a photon, a single wavelength, so we call this photon. We twist that, and the belt curls up, and you get something which is lambda over 4 pi. If in the minimum energy configuration, the field is maximally distributed, which is lambda.
Have you thought about relating this to fractional charge in chromodynamics, Lou's got this fantastic bit where if you cut a Mobius band along the middle, it turns into a trefoil knot, and perhaps the loops on that can be thought as the fractional 1/3 charge that you get in quarks.
I've not actually thought about that. I've written a thesis about it.
Oh, okay, fantastic. And then the last question, I'll ask you a lot more offline, but with relation to the crystals, do you think it might be possible to derive a natural theory of crystal configurations on the basis of the orbitals and relate it to this algebra, this the dimensionality?
One of my collaborations is with some chemists, and we're working together at the moment to start trying to design new materials. So the first thing we're looking at is high temperature superconductivity, a new theory of that, and why that works. But actually the main thrust is to think about how to design room temperature superconductors. So what is about them that's necessary? Could we engineer that? And I think we can. So yes, one does think about new materials here, about how to. The essential thing one has to do is one has to produce a proper environment for dielectrons. So dielectrons repel one another because they have the same charge. So they need to be in a system where that charge is neutralized by sitting in a matrix of positive ion cores like in a crystal. So yes, this is that tool which is needed for the next, because the theory that you have at the moment, BCS theory, for example, is really quantum mechanics sitting on top of quantum mechanics. It's a very primitive theory. You can't really think with it because you don't know what your Cooper pairs are. This thing tells you what your Cooper pairs are. They're dielectrons, they're things which are actually really on top of one another. This comes in the discussion about the reason why it's treated as we didn't reach the whole. But it's something I could talk on because I've got to just on that. Yes, no, thinking that the aim here is it's been difficult to get this stuff out into the mainstream physics. People sort of just haven't done it, and people have their own ideas, and of course, everybody has. So the idea is to do some proof by engineering, actually start building things that work, and it can't really work any other way. So you could achieve license and using this new theory, just you can't imagine that because people can't how to put it together. So yes, that's the part of the plan. That's part of what is going to be about, but it's not engineering.
Thank you.
Okay. Any more questions from the room?
I think Albrecht.
Albrecht, okay.
You need to unmute yourself, Albrecht.
Yeah. You are still muted.
Okay, you have mentioned several times Maxwell. The Maxwell is without any doubt a very elegant system, but unfortunately it is not physically correct because it has the symmetry between electric and magnetic phenomena, but this symmetry does not exist because we have an electric charge but not a magnetic charge. Magnetism is, as we know now, a relativistic perspective of the electric field. But that is not reflected in these theories. So I think it's a warning. There are elegant theories in general, but they have to be checked that they really reflect physics.
Albrecht, would you like to know why this going magnetic charge?
There is no magnetic non-reflectivity one. That's the impression which we have. It was the impression of Maxwell, but it was wrong. You know the book, it's a very famous book of Rosa. It's an English, it's written in the 1950s. He has used the Coulomb law and the Lorentz transformation, and with only these two things, he has deduced the full Maxwell theory. More was unnecessary. There's no magnetism. Magnetism is a side effect. It's similar to the Coriolis force. The Coriolis force, as we know, is also not a true force. It's an
Albrecht, you're wrong. But there is no electricity and magnetism. There is electromagnetism. They're the same thing. So if you look at an electric field in a different way, you get a magnetic field. It's a 6-component object. You're trying to divide these things artificially. That might have been the way that Maxwell did it, but we are 150 years past Maxwell. And you're right, there is some symmetry there, but the symmetry is not really there. Because the symmetry, because the two things, as Dennis was just saying, magnetic fields are really things that make things go round and round in circles. They're space systems, whereas electric field is a space-time particle. There are three space-time parts, x, t, y, t, and z, and not four. And there are three space-space parts, x, y, y, z, and zx, and not four. But there are six components of the electromagnetic field.
In the formalism, but not in the physics.
If you want to go back and argue with, if you were Maxwell and I was Tate, then we could have this discussion and this would be a sense of life. If you are not Maxwell and I'm not Tate, we're sitting in the 21st century, and if you want to argue on that basis, yes, you might have some point. In current understanding of electromagnetism, you're simply wrong. Electricity and magnetism are the same thing. That's been well known for a long time, for really a very long time, since the time of Einstein. So trying to set up a system in which that's not the case and then argue as a problem is a waste of time.
You can look, I can tell you, textbooks about popular textbooks about relativity, and they explain it in the way I said now. And it's ignored because the formalism of Maxwell is
Anybody can write a book about stuff they don't really understand.
Because, Frank, this is books about
Right. I'm getting very uneasy feeling here because of this discussion. Can we cut it at this point, because I don't think you are ever likely to come to an agreement being on very differing standpoints. Are there any questions here from the room or from Zoom? Because we are all also getting a little bit tired after the morning and it's quite hot here.
I'm hungry.
Oh, hungry, yes. Yeah. Okay. Everybody, I think offline you are likely to get more questions or comments, but I think we are now getting to the exhaustion point in the morning. So do excuse us. I would like to thank you again. And thank you all the speakers and discutants for this morning contribution. And we will reconvene about 3 p.m. Yes? So we will be here a little bit earlier to make sure, so 5 to 3 on the Zoom. Yeah? Okay?